Welcome back to another lecture on steel structures. We were designing a built-up column consisting of two rolled I sections, which was to carry an axial load of 1000 kilonewton along with a bracing system. So the I sections with which the built-up column is to be constructed is chosen as ISMB 300, and the distance apart which these two I sections would be placed in the built-up column was calculated to be 110 millimeters. The design of lacing was also done. We had adopted a single lacing system which is inclined at an angle of 45 degree with the axis of the column, of the built up column. The effective length, the width of the lacing as well as the thickness of the lacing were also calculated. Now all these checks for slenderness ratio, the calculation of the dimensions for the lacing has been done in previous two videos. I will provide the link of those two videos in the description box. Okay, you can go and check them as well. Now, in this video, we are going to design the end connection and we are going to calculate the compressive strength and the tensile strength of this single lacing system and find out whether these strengths, that is the compressive strength and the tensile strength, is sufficient enough to resist the force which is acting on the lacing due to the axially compressive load, that is 1000 kilonewton. Okay, so let's move into the calculations. So first what we have to do, we have to determine the design compressive stress in order to determine the design compressive strength of the lacing. So straight away go to page 34 of IS 800 2007, clause number 7.1.2.1, and there you will be able to find the design compressive stress, all the formulas which are related to the calculation of this FCD, which is the design compressive stress, and simultaneously if you multiply this FCD with the effective area of the lacing flat which you have chosen, you will get the design compressive strength. So what you have to do, you have to calculate. Okay, so we have come to the code, and before calculating FCD you have to calculate certain parameters, that is phi, you have to calculate lambda, you have to calculate FCC. Now what is FCC? FCC is Euler's buckling stress given by pi square E divided by KL by R, KL by R whole square. Okay, now what is KL? KL is nothing but the effective length of the lacing, which is taken as 466.7. And what is R? R is the radius of gyration, okay, which is equal to TW divided by root over of 12. So in our previous calculation, as you can see, we had calculated the slenderness ratio for lacing as 134.72. How did we calculate? We first determined the radius of gyration for this lacing plate. Okay, so radius of gyration for this lacing plate is T by root over of 12, where T is the thickness of the lacing flat, and this is how we had calculated R. R is equal to root over of moment of inertia divided by area. Moment of inertia for a rectangular section of the lacing is equal to BT cube by 12, where area is B into T. B is nothing but 50 and T is equal to the thickness, that is 12 millimeters. So R is T by root over of 12, where T is 12. And what is the effective length? This effective length value has been calculated in the previous videos. You can go and check them. LE was calculated as 466.7. So this is how we were getting the slenderness ratio, that is KL by R. Okay, KL by R, L by R is equal to how much? KL is 466.7, 466.7, and divided by how much is R? R is nothing but 12. I'll better write it down. R is nothing but 12 divided by root 12. So if you calculate it, this is the value 134.72. This is the value which is equal to KL by R, right? So put this value 134.72 in your formula. excuse me for a moment. Okay, so put the value 134.72 in this KL by R. You know what is pi, you know what is E. E is equal to 2 into 10 to the power 5. Okay, so you will be able to calculate FCC. Now lambda is equal to root over of Fy by FCC. So Fy is 250 and FCC is equal to this value. Okay, and then again, let me just show you the calculation. Okay, so you are getting lambda is equal to 250 divided by 108.76. Now this is the value of FCC. This is equal to 1.516. Okay, next thing which you have to calculate is you have to calculate phi, right? And what is the formula for phi? Phi is equal to 0.51 plus alpha into lambda minus 0.2 plus lambda square. Okay, so what is alpha? Alpha is the imperfection factor which is given in table 7. Now for this case, I have taken the value of alpha as 0.49. So you can just go back to table number 7 of IS 800 and find this value. So phi is 1.97 and simultaneously I have calculated this value. Okay, so that the value of my FCD was coming out as 70.45 megapascal. Just do the calculation serially and it will be very easy for you to calculate FCD. So once I've calculated a FCD, now I will be calculating the design compressive strength, which is equal to area of lacing, that is 12 into 50 into FCD, that is 70.45, and my design compressive strength is coming out to be as 42.27 kilonewton. Now what you have to do, you have to calculate the force that is acting along or acting on the lacing, rectangular flat, on the lacing flat. So how do you calculate F? See, for calculating F, first you have to calculate the transverse shear force which is acting on the lacing. Okay, and how much is it? Transverse shear force. Okay, I have to go back to the clauses for lacing. Okay, so as you can see that the lacing shall be proportional to resist a total transverse shear Vt at any point in the member equal to at least 2.5% of the axial force in the member and shall be divided equally among all transverse lacing systems in parallel plane. So Vt, which is the transverse shear force, is equal to how much? 2.5% of the axial force. Okay, Vt is 2.5% of the axial force in the member and it should be divided equally among all the transverse lacing systems in parallel plane. So in single lacing system we have two parallel planes. Okay, we have two planes, and for this, because of the presence of two parallel planes, we have to divide the value of Vt by the number of planes, that is by 2. Okay, so Vt will be acting in the horizontal direction because it is the shear force. And how to calculate Vt? It is equal to 2.5% of P. And how much is P? P is our factored axial load, okay, which is equal to 1500 kilonewton. This is already given in the problem, right? So if you calculate it, the value of Vt is coming out to be 37.5 kilonewton. Now it has been also said that for the number of planes, okay, depending on the number of planes which are there for the lacing system, you have to divide the value of Vt divided, you have to divide the value of Vt by the number of planes. Okay, so Vt by n in case of single lacing system, number of planes present is 2. Okay, for single lacing system, number of planes is equal to 2. Okay, and hence transverse shear will be equal to Vt divided by this number of planes, which is equal to how much? 37.5 divided by 2. Okay. Now, Vt by n, this value of shear force will be acting in the horizontal direction. And we have to calculate F, which is acting along the direction of the lacing. Okay. So F is acting in this manner. F is acting in this manner and Vt by n is acting in this manner. So what you can do is you can form a right angle triangle here. You can form a right angle triangle here. Okay. And this angle is how much? This angle is equal to 45 degree. See, this is theta and the theta here is equal to 45 degrees. So what you can write, you know this value, you don't know this F value. So you can write sine theta is equal to Vt by n divided by the hypotenuse, which is given by F. Okay, so this is how you will be able to calculate the value of force which is acting on the lacing or along the plane of lacing. So F is equal to Vt by n divided by sine theta. And if you calculate, the value is coming out to be as, let me write it down. This is equal to, what is Vt? Vt was calculated as 37.5. Okay, divided by 2, and this entire thing sine theta, sine, how much is theta? So theta is 45 degrees. Okay, and the value of S is coming out to be 26.5 kilonewton. Simple. Now you have to compare this externally acting force in the lacing. Okay, the amount of force which is acting on the lacing is given by F equal to 26.5. Now, if you compare this value with the design compressive strength of the lacing, okay, the design compressive strength is an inherent strength of this lacing system. Okay, you have to see whether this strength is enough to resist the force which is acting on the lacing, right? So what was our design compressive strength? It was equal to 42.27. So this value of F is clearly less than the design compressive strength, hence it is safe in compression. Okay, simple. Okay, the next thing which you have to do is calculate the tensile strength. Okay, the tensile strength of the lacing bar should be calculated with respect to the two criteria. First is yielding due to cross section and rupture of net section. So for the first case, we have TDG, that is yielding due to cross section. Design strength due to yielding of cross section is equal to AgFy divided by gamma m0. What is Ag? Ag is the gross sectional area of the lacing bar, which is equal to 12 into 50. Fy is 250, and gamma m0 is the partial safety factor, which is equal to 1.1. So this value is coming out to be 136.36 kilonewton. For rupture due to net section, the design strength is 0.9 AN FU divided by gamma m1. What is AN? AN is the net area of the lacing, and it would be calculated by subtracting the bolt hole, that is 18 millimeters, from the width of the lacing. So the bolt that we had adopted, the bolt dia adopted was how much? 16 millimeters. Bolt dia is equal to 16 millimeters, and hence the bolt dia hole will be equal to 16 plus 2 mm, that is equal to 18 millimeters. Okay, so the net area will be how much? 50 minus 18 into 12. This is the net area, and FU is 410. Gamma m1 partial safety factor is equal to 1.25. So TDN is coming out to be 133.36. Okay, so we are deliberately ignoring the design strength due to block shear failure, because the value of block shear failure, the value of design strength due to block shear failure is generally higher compared to these two values. So what is the tensile strength of the lacing bar? It will be equal to least the least value between these two. Okay, so the least between these two values is how much? 133.36 kilonewton. Okay, so this 133.36 kilonewton is the design tensile strength of the lacing bar, and that value is much lesser than the force which is acting on the lacing, which is equal to 26 kilonewton. Hence the lacing bar, the system of lacing which we have adopted, is safe in compression and safe in tension. That is, it has adequate compressive strength as well as tensile strength to resist the axial load of 1500 kilonewton coming on it, coming on the built up column. Now when we are done with the slenderness ratio check, with the compressive strength test check, and the tensile strength checking, lastly what we have to do, we have to design the end connection. Okay, now we had already adopted the bolt dia as 16 millimeters. Okay, so the based on that we have to design the end connection, right? Okay, so in order to design the bolt, or is design the connection system of the bolt, we have to calculate the shear strength of the bolt and the bearing strength of the bolt. Now if you see IS 800 2007, you will be able to find this formulas. VDSB, which is the design shear strength of the bolt, is given by this: FUB by root over of 3 gamma MB into ANB NN plus ASB into NS. Now whenever you are considering a bolt, okay, you will have two portions in a bolt, right? So the circular portion here, the circular portion, this is the circular portion here, this is known as the body or the shank, and the area corresponding to this shank is written as ASB. Okay, the area corresponding to this shank is ASB, and the other portion consists of roots. Okay, this point is known as a root. Okay, ROOT, root. Okay, the area corresponding to this root section, okay, the area corresponding to this root section is denoted as ANB. Okay, this area is denoted as ANB. Clear? Now we will be assuming that the failure plane is passing through this root portion. Okay, and hence the n, what is NN? NN is the plane, the failure plane passing through the root portion. So we are considering that the failure plane is passing through this root, hence NN is equal to 1 and NS is equal to how much? It is equal to 0, right? And how much is ANB? ANB is the net dia of bolt, which is at the root area, which is the root area. This is taken as 0.78 times AG or AS. AG is the cross sectional area, and AG and ASB are same for a bolt. Okay, so ANB is equal to 0.78 times AG. And what is AG? AG is pi by 4 into 16 square. This is the main diameter of the bolt, and it is coming out to be 157. So we are taking NN as 1. NN is the number of failure plane passing through the root section, and ANB is the area in the root section, area of the bolt in the root section. So this is equal to 157. This is 1, and you put the value of FUB as 400, gamma MB as 1.25, and VDSB is coming out to be 29 kilonewton. Clear? Now next thing is you have to calculate the bearing strength of bolt, or VDPB. Okay, VDPB is equal to 2.5 into KB into D into T into FU by gamma M1. Now what is D? D is the diameter of the bolt, and what is T? T is the thickness of the lacing plate. Okay, D is diameter of bolt and T is the thickness of the lacing plate. FU is 410, gamma M1 is 1.25. Now the thing which you have to calculate is KB. Okay, you have to calculate this factor KB. Okay, now there are 4 criterias which should be which with respect to which kb has to be calculated. Okay, what are they? First we have E by 3d0, right? Next we have P by, okay, so kb will be calculated by 4 cases, according to 4 cases. First we have E by 3d0. What is E? E is the edge distance or the end distance, which is taken as 1.5 times the hole diameter. Okay, E is taken as, E or the edge distance is equal to 1.5 times hole dia. Okay, I can write it as d0. So how much is your hole dia? I have taken here the hole dia as 17.5, but you can also take it as 18, no problem. So edge distance I have calculated 1.5 into 17.5 and 3 into d0. D0 is nothing but the hole dia. That is again 17.5. So it is coming out to be 0.5. Okay. Then we have the second case we have is FUB by FU. FUB is the ultimate strength of the bolt. FU is the ultimate strength of the steel, the built up column section, for the built up column. So that is 400 by 400 divided by 410, which is equal to 0.976, much greater than E by 3d0 value. Then we have P by 3d0 minus 0.25. So P is nothing but the pitch distance, which is taken as 2.5 times the diameter of the bolt. Let me write it down. P is the pitch is equal to 2.5 times diameter of bolt. Okay, so this one is coming out as 40 divided by 3 into 17.5. D0 is the diameter of the hole minus 0.25. So this value is coming out to be 0.51. And we have the fourth case as 1. So the value of kb should be the minimum among these 4 values. And what is the minimum value? The minimum value is for E by 3d0, which is equal to 0.5. So you put all the values. You put all the values here. Okay. Here there should be, just give me a moment. Okay. There should be a 2.5, right, into kb, which is 0.5 into 16, which is the diameter of bolt. T is the thickness of lacing. Fu is 410 and gamma m1 is 1.25. So that value is coming out to be 31.5 kilonewton. Now, again, for the bolt, the design strength will be the minimum among these 2 values, that is VDPB and VDSB. This is VDSB. Okay, so which is the minimum value? The design strength of bolt is taken as 29 kilonewton. Clear? Now what you have to do, you have to calculate the number of bolts which needs to be provided at the 2 ends of the lacing. So for finding the number of bolt, what you must do, you have to divide the force which is acting on the lacing. Force that is acting on the lacing, let me write it down. Force acting on the lacing, which is equal to how much? It is equal to 26.52. You have calculated this earlier. Okay, you have to divide this value by the design strength of bolt. Okay, which is equal to what? This value, the minimum among VDSB and VDPB, that is equal to 29 kilonewton. Okay, so if you calculate, the value is coming out to be 0.914. Okay, so you cannot provide 0.914 bolts in lacing. So what you have to do, you have to provide 1 bolt at each ends, right, of the lacing. You have to provide 1 bolt at each ends of the lacing. Let me just show you one diagram. So this is how you should provide the bolt. At this end of the lacing, you will provide 1 bolt, and at this end of the lacing, you have to provide another bolt. So that is it. The entire design problem for built up column along with lacing is done. So if you have come along all through the video, then I would kindly request you to subscribe to my channel for getting updates on more videos like this on steel structures. So if you enjoyed it, please give a thumbs up, and for any doubts or any suggestions, you can write them in the comment section.